Hi, I'm Robin Goldstone, and I really, really, really like to use my own laptop. No, actually, I am Robin Goldstone. I work at Lawrence Livermore National Lab in the HPC Advanced Technologies Office, where I'm responsible for participating in strategic planning for next-generation HPC and data-intensive computing platforms. Today, I'm going to be talking to you about Coral, the collaboration between NNSA and DOE that's delivering LLNL's next-generation supercomputer called Sierra, and then a little look at what's coming after that. So first, I'll start with a little background about LLNL and our mission. Then I'll tell you about the Coral collaboration, why we did it and what we achieved. And then I'll provide an overview of Sierra, which is LLNL's Coral system, which will be delivered in 2017. And since 2017 is just around the corner, we're of course already looking ahead to what's next, and I'll be talking about that a little bit as well. So first, about Lawrence Livermore. If you're not familiar with Lawrence Livermore, it was established in 1952 at the height of the Cold War to meet urgent national security needs by advancing nuclear weapons science and technology. Today, we apply our world-class talents in science, technology, and engineering to a much wider range of important problems in the area of national security. This includes maintaining our nuclear stockpile deterrent, as well as new challenges in the area of nuclear non-proliferation, biosecurity, counterterrorism, and energy and environmental science. And from the beginning, supercomputing has been a core capability supporting laboratory missions, and it remains so today. The lab supercomputers are used to perform complex simulations of scientific phenomenon ranging from the atomic scale up through large, complex multi-physics systems. Every generation of supercomputer enables us to explore these phenomenon in more detail, or in some cases to solve problems that were previously unsolvable. LLNL is part of the National Nuclear Security Administration. NNSA is a semi-autonomous agency within the U.S. Department of Energy responsible for maintaining and enhancing safety, security, and effectiveness of the U.S. nuclear weapons stockpile without nuclear testing. This is known as Stockpile Stewardship. The Advanced Simulation and Computing Program, or ASC, is responsible for delivering the simulation capabilities that are needed to meet NNSA's mission to annually assess and certify the nation's weapons stockpile. ASC delivers not just the computational platforms, but the weapons codes and the science behind them. Through modeling and simulation, ASC allows us to use computation as a surrogate for nuclear testing. Our ability to model complex nuclear weapons systems provides us with the confidence to certify the performance of our aging stockpile, as well as gain a comprehensive understanding of the weapons life cycle from design to dismantlement. And in addition to stockpile stewardship, ASC tools are also used within NNSA and in other government agencies to support other national security missions, including non-proliferation, emergency response, and nuclear forensics. So the simulation codes that are needed to assess the nuclear stockpile are complex multi-physics applications. In the 80s, we went through a pretty significant and painful process of migrating our applications from the vector mainframes of that era to the SMP architectures that are still in use today. As we look ahead to exascale systems in the not-so-distant future, we face the likelihood that our applications are going to have to once again be refactored. This slide shows some of the factors that make this a very daunting task. And we must be able to make the transition to the future while continuing to meet today's mission of performing the annual stockpile assessment. This drives the need for us to explore evolutionary approaches alongside the most revolutionary ones. The expectation is that our existing weapons codes will need to run for the foreseeable future using today's MPI plus X model, while new codes are developed from the ground up, a process that can take 10 years or more. And yes, we will still need Fortran. So ASC has a two-tiered platform strategy in order to meet our mission needs. We have what we call commodity technology systems that are sort of the workhorse cycles across a wide range of scientific workloads. Every few years, we go out to bid and select a single vendor to deliver a boatload of Linux clusters across the 3 NNSA laboratories. Livermore, Los Alamos, and Sandia. These clusters are built using a scalable unit building block model, allowing us to build clusters of multiple sizes for use in different environments and different use cases. We run a common Linux software stack, the TriLab operating system stack, or TOS, across all of these systems. By leveraging a common hardware platform as well as a common software stack across the 3 labs, we were able to achieve great economies of scale. A contract for our 3rd generation commodity clusters called CTS-1 was recently awarded, and we're in the process of getting ready to bring these systems into production over the next 6 months or so. And then the other tier of our platform strategy is the advanced technology, or ATS systems. Historically, these were single systems procured by one laboratory, though when I talk about Coral, you'll see how that's evolving. The ATS systems are designed to meet unique mission needs and run the most demanding NNSA workloads. At the same time, we use these platforms to push the envelope of technology. Combining sometimes bleeding-edge technology with the need to meet important mission needs is a risky proposition. To succeed at this, we depend on strong, long-term relationships with our vendor partners, and we make strategic investments in development and engineering where it's needed. Here's the current Asc Platform Timeline. On the ATS side, the platforms are sited at Livermore and Los Alamos in an alternating fashion. Regardless of location, these systems are used heavily by all 3 laboratories. Sequoia is LLNL's current production supercomputer, a Blue Gene Q system from IBM. As you can see, Sequoia has been in production for several years now and is headed towards the tail end of its production lifespan. Meanwhile, the Los Alamos Trinity system, which is based on Intel Haswell and Knights Landing processors, is well along the road towards full production deployment. Trinity will take over as the primary ATS platform as Sequoia heads off into the sunset. Sierra, LLNL's Coral system, will follow on the heels of Trinity. And planning for the next ATS system at LANL, called Crossroads, is well underway, and then the cycle continues with the ATS4 system at Livermore, which we're expecting to be the first Exascale class system. Then the bottom half of that chart, you'll see the cadence of the CTS systems. Our current systems we call TLCC2. They're based on Intel Sandy Bridge and QDR InfiniBand, and they currently provide the majority of our capacity computing cycles. CTS-1 system will be based on Penguin's Computer's Tundra ES platform with Intel Broadwell processors and a yet-to-be-announced 100-gigabit interconnect. Okay, so let's move on to Coral. So Coral stands for the collaboration of Oak Ridge, Argonne, and Livermore. In 2011, NNSA and DOE's Office of Science signed a memorandum of understanding to collaborate on procuring our next generation supercomputing systems. There's a huge amount of planning that goes into executing an RFP and awarding the contract for a single supercomputing system. All 3 of these laboratories were on track to be ready to receive their next system in the same time frame. And while our missions are not identical, there's enough similarity in our computing requirements to justify working together on a single RFP. DOE established a requirement that each of their 2 leadership computing facilities at Argonne and Oak Ridge have diverse architectures. Meanwhile, LLNL was free to choose whichever solution we felt offers the most value to NNSA. So, as I indicated, Argonne, Oak Ridge, and Livermore worked together to jointly prepare and release a single RFP. We evaluated the responses and selected the top 2 unique architectures. Oak Ridge selected the solution proposed by IBM for a heterogeneous architecture featuring IBM power processors and NVIDIA GPUs. Their system will be called Summit. The contract for Argonne's Aurora system was awarded to Intel. Aurora is a many-core architecture featuring Intel Phi Knights Hill processor. And Livermore ultimately decided to choose the IBM solution alongside Oak Ridge. Each lab's procurement consists of 2 contracts, a build contract for the actual system and a non-recurring engineering, or NRE, contract, which provides funding to the vendor to enhance their solution above and beyond their base system proposal in ways that the lab felt were most valuable. Livermore and Oak Ridge jointly negotiated their NRE contract with IBM in order to maximize the value of our individual NRE budgets. While Argonne's NRE contract with Intel is separate, all three laboratories participate in both the IBM and Intel NRE activities. There may be competition between IBM and Intel. I'm pretty sure there is, but it's not a contest for us. All the DOE and NSA laboratories have a vested interest in seeing both of these approaches succeed. So between the Intel and IBM solutions, Coral allows us to explore the two architectures that are the most likely candidates for future exascale systems. On the left, you see the Xeon Phi approach that's being used on the Argonne Aurora system. This architecture features CPUs with many relatively small homogeneous cores with wide SIMD registers. Given the modest performance of a single CPU, building a very large system may require many nodes on the orders of tens or possibly hundreds of thousands. The processors have access to on-chip high bandwidth memory in addition to standard DDR memory. And on the right, you will see the hybrid multi-core approach like Sierra and Summit, which has a more modest number of very powerful nodes comprised of one or more CPUs tightly coupled with one or more GPUs. The GPUs also have on-package high bandwidth memory, while the CPUs interface with standard DDR DRAM. While each of these architectures has its own unique challenges, they also have some key commonalities. In both cases, there is a need to exploit a large amount of on-node parallelism, whether it's the wide SIMD on the many-core processors or the SIMT style parallelism in the GPU. Both architectures share what we believe will be the biggest challenge, which is the need to exploit a multi-level memory hierarchy. Data movement is costly, and DRAM memory bandwidth is stagnating. This drives the need for high bandwidth memory closer to the processing units. Being able to use this high bandwidth memory is the key to exploiting the performance of both of these architectures. A key question we have to answer is how. Will we be able to count on the magic of compilers and runtime systems to integrate this additional tier of memory transparently, or will applications need to deal with it explicitly? Or can we just fit our entire problem in the high bandwidth memory and ignore the DRAM entirely? An important aspect of the Coral procurement model is a shared risk approach designed to encourage vendors to innovate without having to take excessive financial risk. This might not be that much interest to all the technical geeks in the audience, since it's more a part of the business side of the Coral collaboration. However, it's really an important aspect. We're forming long-term collaborations and contractual partners with these vendors, and we do want them to succeed. The shared risk approach alters the traditional fixed price contract approach. For the build contract, we engage in early contract negotiations to define targets that represent our desired and occasionally stretch goals for the system. These include system characteristics as well as the cost of commodities that we're going to be buying way out in the future, such as memory. For the NRE contracts, we strive for as much lead time as possible and collaborate closely with the vendors to maximize the chance that the innovations we are funding can make it into the final system that they build. Our RFP and subsequent contracts have few mandatory requirements, many target requirements. Targets are performance levels that both parties reasonably believe can be achieved depending on the results of the NRE work. Once a go, no-go decision is made to move forward with the build contract, the targets are converted into traditional contractual requirements that the vendor must meet. We evaluate the level of the system as the achievement of the system as a whole rather than assessment of performance of each target individually. We don't want to set up a situation where a contract fails because a vendor can't meet one specific target requirement. The NRE contracts are closely coupled to the build contracts. NRE results feed into the go, no-go decisions in the build contract, as I mentioned. Vendors must share the cost of the NRE work. We have a 60-40 cost share mentioned there. This results in the selection of mutually beneficial NRE and further incentivizes the vendor to succeed. Livermore and Argonne used this approach successfully with our Sequoia Mira partnership back in 2012, and we expect this to be a successful model again for Coral and potentially for all future DOE and NSA collaborations. I mentioned the use of target requirements. Here are the highest priority target requirements that we established for the Coral system. Our main performance requirements are expressed as speedups over current systems based on a diverse set of benchmarks that we provide. In LLNL case, these speedups are relative to Sequoia. For Oak Ridge, they're compared against Titan, and at Argonne against Mira. The other targets you see here reflect our growing concern over power consumption and system reliability. The Coral benchmarks represent a broad range of applications expected to dominate the science and mission deliverables of the Coral systems. Benchmarks are divided into several categories. We have scalable science benchmarks, which are full applications that are expected to scale to a large fraction of the Coral system. They're typically single physics applications designed to explore specific scientific domains such as material science or combustion. Throughput benchmarks represent particular subsets of applications that are expected to be used as part of the everyday workload of the scientific applications on the Coral systems. In particular, uncertainty quantification, or UQ, is a driving mission need for the ASC program, where the workflow involves ensembles of hundreds or thousands or more of related calculations. Each individual run in a UQ ensemble requires relatively modest scaling. Priority is placed on minimizing this ensemble's overall throughput. Then we also have these skeletons and micro benchmarks. These are designed to reproduce the memory or computational patterns of physics applications or packages, make little or no attempt to investigate numerical performance. They're useful for targeting investigations such as network performance characteristics at large scale, memory access patterns, thread overheads, bus transfer overheads, system software requirements, I/O patterns, et cetera. They're designed to stress the system in very specific ways. I mentioned that once Oak Ridge and Argonne had made their selections, LLNL had the luxury of being able to pick whichever system we believe would best meet NNSA mission needs. We chose the IBM solution in part based on the outstanding benchmark analysis that was done by IBM and NVIDIA. Not only were they able to demonstrate they could meet the requisite performance targets, but they were able to show us how this could be achieved using minimally invasive annotations like OpenMP. As I mentioned previously, given the size and complexity of NNSA's multi-physics applications, it's unlikely that we're going to be able to employ heavy-handed code changes such as rewriting kernels in CUDA. Our codes have to be portable so they can run across other ATS systems as well as on our commodity clusters. Hard coding changes for a specific architecture is very undesirable to us. Okay, so what are we getting anyway? So here's some aspects of the Sierra system that I can share with you. Some of them are still protected under NDA, so I might be a little vague in some places. The Sierra building block is a node containing one or more IBM Power 9 processors coupled with some number of NVIDIA Volta GPUs connected by NVIDIA's new NVLink high-performance interconnect. There is a lot of memory on these nodes, over 512 gigs per node, counting both the DDR4 attached to the power processor as well as the high bandwidth stacked memory on the Volta GPUs. A key architectural feature of this solution is coherent memory between the CPU and the GPU. Having to explicitly move data between the GPU and the CPU over a PCIe bus has historically been a reason that LLNL has shied away from GPU-based systems. The coherent interface provided by NVLink is not entirely a panacea, but it's definitely a big deal, turning a problem of correctness between two disjoint memory spaces into one of how to get good performance across the two. The Sierra nodes will also have around 800 gigabytes of SSD storage implemented using the new NVM Express standard, which defines an optimized interface and feature set for PCIe attached flash devices. The SSD storage will be used to implement a burst buffer solution as part of our NRE contract with IBM. Then some number of nodes will be packaged into some number of racks, resulting in a system with a peak performance in the range of 120 to 150 petaflops and consuming around 10 megawatts of power. The projected power consumption for Sierra is actually quite modest by our standards. It's just a little more than the 9.6 megawatts of power that we're already providing for Sequoia. The challenge is not whether we can plumb 10 megawatts of power into our building and deliver it to Sierra. The challenge will be how to deliver the power where it's needed the most to get optimal performance out of the system. The interconnect on the Sierra system will be dual-rail Mellanox EDR InfiniBand. This is one of the lower risk components of the proposed solution, given that EDR is basically already shipping. However, it's actually a part of our ATS strategy. We can't have every last component of the system be high risk. We actually want some components to just work right out of the box. We have to choose where we take risk based on opportunity for reward. The parallel file system for Sierra will be IBM's GPFS product. The capacity and bandwidth numbers shown here may not stand out as particularly impressive, but again, this is by design. We're fully committed to making use of the burst buffer technology that we're developing for Coral. We believe that a properly designed burst buffer solution, which includes integration with the job scheduler and the applications, should not just serve to insulate applications from the impact of slow I/O, but rather to actually eliminate writing some amount of data all the way out to the file system. Checkpoints, also known as defensive I/O, are meant to preserve the state of an application so that it can recover from system failures without having to start over from the beginning. Once a job completes successfully, most of these intermediate checkpoints are deleted from the file system. A non-volatile burst buffer, which provides both fast and safe storage closer to the processor for checkpoints, can therefore take the place of the file system entirely for this type of I/O. NVRAM is expensive, and so is the burst buffer solution. In order to ensure that we use it effectively, we purposely reduced both the capacity and the bandwidth requirements for the parallel file system. The little open power box down there is actually pretty important as well. I'll talk more about that in a few minutes. So here's a little more detail about NVIDIA's technological innovations that are going into the Volta GPU. As I mentioned, NVLink will provide a high bandwidth coherent interface between the GPU and the power processors. And 3D stacked memory on the GPU offers large improvements in bandwidth capacity as well as energy efficiency. And here's a high-level overview of the Coral software stack. One-offs like Sierra met our needs, but they were not tied to vendor product roadmaps. For Sierra, to the extent possible, we're leveraging IBM's mainstream product roadmap and much of their standard Linux cluster software stack. Through our NRE contracts, we're collaborating closely with IBM to add value to their standard product offerings in the areas that are listed here. One specific aspect of the NRE contract that I've been involved with has to do with the operational challenges of managing huge amounts of diagnostic data that these systems generate. This includes node health and environmental data, system logs, job-specific error logs, interconnect error messages, file system errors, etc. From an operational standpoint, trying to identify the root cause of a problem on one of these systems can be like trying to find a needle in a haystack. It's a big data problem, and we're working with IBM to apply popular big data technologies towards solving it. In addition to isolating failure causes after the fact, this approach will set the stage for us to perform more proactive failure prediction and avoidance. If we do it right, our sysadmins should get much more sleep at night. One other thing that's worth mentioning is the Coral NRE contract requires that all new software developed under the contract be open source. This will ensure that innovation developed for Coral can benefit others as well. The previous slide listed some of the software NRE being developed for Coral. This slide includes some additional hardware-focused items as well as a center of excellence, which I'll talk about next. The Coral NRE collaboration is proving to be a highly productive exercise in co-design. We have 8 working groups comprised of vendor reps and lab technical staff. I've watched firsthand how several of these working groups have evolved from somewhat awkward and skeptical interactions into truly collaborative partnerships. I'm extremely proud of the work that we've accomplished together with IBM so far, and we're not done yet. So the Sierra Center of Excellence is proving to be another highly successful outcome of the Coral collaboration. Oak Ridge used the Center of Excellence concept successfully for Titan, and it was adopted for use both by Trinity and Coral. For the Coral IBM systems, Livermore and Oak Ridge each have established a Center of Excellence where computational scientists from IBM and NVIDIA work closely with our application scientists to develop tools and technologies that will optimize the codes and achieve the best performance on the Coral systems. early application code innovation executed in tandem with systems development allows important two-way feedback between the system developers and the application writers. This will ensure that ongoing system will work correctly and effectively to support our necessary applications. So here's some specific goals that have been established for the Sierra Center of Excellence. We're pretty much starting from square one when it comes to programming GPUs. So the initial efforts are focused on helping our application folks understand the fundamentals of GPU programming and begin thinking about how to port their codes. This will evolve into consideration of programming models, identification of algorithmic changes required, and ultimately trying these things out on early access Sierra hardware. While Trinity doesn't use GPUs, its KNL many-core architecture does share some of the same programming challenges as I mentioned earlier. Our applications need to run on both of these platforms, so to that end, we stay closely involved in the Trinity COE projects in addition to our own. So here's a look at how we see the different centers of excellence fitting together. We have the two NNSA centers of excellence, one for Trinity and one for Sierra. Then we have the two of the DOE centers of excellence, one for Cori and one for Summit. Trinity and Sierra have a shared mission, and so do Cori, Summit, and Aurora, okay? Trinity and Cori share the same architecture, as does Sierra and Summit. And there's also the need for each lab to track the other architecture for risk mitigation purposes. So I think it's fair to say that we're all in this together. Whew, that was a complex slide to get through. Anyway. Okay, so let me say a few words about open power. Sierra is not going to be the lockdown proprietary IBM system of old. Instead, it's a collaboration between IBM, NVIDIA, and Mellanox formed under the umbrella of the Open Power Foundation. IBM created the Open Power Foundation in August of 2013 with the intent to open up the technology surrounding the power architecture in order to build a rich ecosystem of power-based solutions. I found a quote from Dave Turek at IBM who said, "We could not have bid for Coral without open power. It would have cost us hundreds of millions of dollars and taken us years." Livermore and Oak Ridge are really hoping to see open power succeed long term. Open power benefits IBM, it benefits us, and the ecosystem that we're helping to build through Coral will benefit a much broader community. Okay, final words on open power. This is not quite as dense as Gilad's slide, but it does take more than just a good processor to succeed in the HPC marketplace. Ecosystem enablement is a key goal of the Open Power Foundation, and as you can see, that ecosystem is starting to take shape. Okay, so what's next? Sierra will be delivered in 2017. I'm personally hoping that I'm retired by the time the next system hits our floor, but life will go on without me, and no one is resting on their laurels. So I want to go back to our mission for a minute. I realize not everybody is all that enthusiastic about our mission. Many people would prefer that we did not have nuclear weapons. In fact, I think most people would prefer that, myself included. But in other parts of the world, nuclear weapons are all the rage. And for that reason, having a nuclear deterrent is perhaps not such a bad thing. With that in mind, here's some things to consider about what we need to do at NNSA and why it is so challenging. In the past, the final judgment about safety, performance, and reliability of the country's nuclear weapons stockpile was confirmed by nuclear test results. Because of this, we could get away with computer models of modest complexity. Today, we no longer have the ability to do nuclear testing, and that is no longer our final arbiter. And we have weapon systems that are aging beyond their designed lifespan. The story I like to tell goes like this. Imagine you have a race car in your garage. It's 30 or let's say it's 40 years old, okay? You can go out in your garage anytime you want, you can look at that car, you can touch it, you can kick the tires, but you can't start it up and you can't drive it, okay? One day, you walk out into your garage and there's a puddle of oil under the car. You see that a hose has a leak. you head on over to AutoZone and discover that they no longer make hoses for 40-year-old cars anymore. They have some new hoses that might not work, and you're welcome to try to install one, but remember, you can't start up the car. And oh, by the way, at any moment, the President of the United States, maybe even President Trump, can call you on the phone and tell you to open up your garage and start that car up and drive 80 miles an hour down your driveway. Every year, you have to promise him that you will be able to do this at a moment's notice, anytime he calls you. And if you're wrong about your ability to do that, you will be in big trouble, okay? So in this era, scientists must rely much more heavily on modeling and simulation to understand the complex aging process of the weapons components and the weapon systems as a whole in order to certify that our nuclear weapons stockpile is safe and reliable. In many cases, our understanding of basic scientific phenomenon, whether through theory or experiment, is limited. More capable computers aid us in improving accuracy of the analysis of materials properties, improving models for known physical processes, identify and modeling missing physics, quantifying uncertainty, and improving the performance of complex models and algorithms in macro-scale simulation codes. And in addition to stockpile stewardship, as I mentioned, the lab's national security mission space has grown in recent years to include nuclear non-proliferation and counterterrorism. The challenges we face as a nation will continue to drive growth and demand for more powerful computational capabilities. As our challenging scientific problems continue to grow, so do the challenges of producing larger, more powerful computers. These include creation of more energy-efficient circuit, power, and cooling technologies, increasing the performance and efficiency of data movement, integrating advanced memory technologies to improve both capacity and bandwidth, developing scalable system software that is power and resilience aware, inventing new programming environments that express massive parallelism, data locality, and resilience, and creating data management software that can handle the volume, velocity, and diversity of the data that is anticipated. Okay. So in the absence of a formal Exascale program, DOE and NSA have been piecing together a number of separate efforts to tackle these challenges. This includes the D&E funding that I mentioned for Coral as well as Trinity. It includes the Fast Forward and Design Forward research programs, which are focused on critical technology and platform R&D respectively. The Office of Science funds research programs focused on software environments, and both DOE and NSA have their respective co-design centers. These efforts have all been chipping away at the challenges, but we really need a more holistic approach. So it finally appears there might be enough momentum to put in place a full-fledged Exascale program. They've been referring to this as the Exascale Computing Initiative, or ECI, though once funded, it will actually be called the Exascale Computing Program, or ECP. So once again, this is a joint activity between DOE and NSA's Office of Science, and the goal is to pull together all the independent activities I described on the last slide into a single comprehensive program that includes hardware, software, applications, data, and the underlying math and computer science. It will build upon the success of the Coral collaboration to engage in close partnerships with industry to design productive systems based on marketable technology. A set of key performance goals has been established for this Exascale system. We keep saying that we don't care about flops anymore, but apparently an exa-op of performance is still desirable, though it's unclear how that will be measured. And we're still drawing the line in the sand about staying under 20 megawatts. Ideally, this system will be no less reliable than today's systems, despite the expectation of significantly more components. And there's an admirable desire to maintain or improve productivity. Also, as you can see, they've adopted the benchmarking methodology that was used by LLNL on Sequoia and carried forward to Coral, where performance is evaluated by some X speed up over previous systems using a diverse set of benchmarks. So here's a high-level view of the planned ECI org structure, showing a breakdown into 4 main project areas: software technology, hardware technology, applications, and Exascale systems. Planning is actually further along than this chart shows. There's been directors identified for each of the projects, a budget's been developed, as well as a detailed execution plan, but unfortunately these more detailed plans are not public yet, so you'll just have to take my word for it. And here's a notional timeline showing the evolution of each of these project areas and culminating with the delivery of an Exascale system around 2023. Several hardware prototypes are expected over the next few years, plus the A2 system, otherwise known as LLNL's ATS-3 system, the follow-on to Trinity, and the system labeled A3 in this picture potentially corresponds to the LLNL ATS-4 system, the follow-on to Sierra. Okay, the end. No, it's not the end. I want to talk about the end game in all of this. So I've talked a lot about LLNL's Stockpile Stewardship mission, but our expertise and our computing capabilities are applied across a wide range of scientific disciplines. One example is the development of Cardioid, a state-of-the-art heart simulation developed in collaboration with IBM. The goal of this effort was to be able to simulate the electrical behavior of heart cells at higher resolution and for longer duration than could previously be done in order to better understand the mechanisms that lead to arrhythmia. The Journal of the American College of Cardiology reported in 2006 that about 2 of 1,000 people worldwide die of ventricular arrhythmia every year. It's the most common cause of sudden cardiac death. Predicting who will die suddenly from a ventricular arrhythmia is a huge challenge. At the time the Cardioid project was started, computer simulations that could potentially help cardiologists find effective therapies took hours or even days to simulate a single heartbeat. Developing a faster simulation of the electrophysiology of the human heart could enable cardiac specialists to model how patients would react to certain drugs and how generic variations predispose some patients to arrhythmias. So the Cardioid project leveraged the expertise of the joint IBM-LLNL team of scientists and computer scientists together with the massive capabilities of the Sequoia Blue Gene Q platform. This slide lists the extensive and innovative optimizations that were performed to improve the performance of the code. I'm not going to go through all of them, or any of them actually. But if you look down the list, you might recognize that some of these techniques are ones that will be needed to exploit the massively parallel systems of the future. So our experience optimizing apps like Cardioid for Sequoia should help us going forward. The result of these optimizations was a code that was able to achieve both an impressive percentage of the Blue Gene Q peak as well as near perfect strong scaling. A simulation of 1 hour of normal heart activity could be done on Sequoia in 7 hours. Previous codes took 45 minutes to simulate a single heartbeat. So here's a little movie that highlights the orders of magnitude improvement in performance that Cardioid has achieved over previous state-of-the-art heart simulations. This is a very sophisticated movie, get ready. Okay, so the red dot represents the progression of Cardioid over 1 minute of wall clock time, during which 18.2 seconds of simulation is achieved. The blue dot shows the progress of the previous state-of-the-art simulation over the same time period. You have to watch the blue dot pretty closely to see it move. It's moving, I guarantee it is. But ultimately, each generation of supercomputing opens the door to more and more profound scientific discovery. And this is what motivates us, at least myself anyway, to continue to push forward towards Exascale and beyond. So we'll stop the simulation. Believe me, it ends eventually. All right, well, that's all I have, so thank you very much.